Hi, my name is Kruthik Alapati, and this is my Lab 5 on the motion of a drop slinky. So the objective of this lab was to create a model predicting the motion of a falling slinky using a computational model on GlowScript and comparing it to an observational model of the falling slinky in real life that I tracked on Tracker. So why is this important? Well, Newton's second law can be used to describe the motion of the falling slinky. And this is because Newton's law states that the rate of change of momentum over a body of time is directly proportional to the force applied and occurs in the same direction as the applied force. So if we can map out all the forces, then we can track the motion of the slinky throughout the model. So you can see here that we have Newton's second law, F equals ma, and that can be changed using the momentum principle to get the velocity update principle. And then we have the net force in terms of the components of the net force, which is the force of gravity, the force of drag, and the force of the tension of the slinky, which I'll explain further in the next slide. So the force of gravity is the mass times gravity in the negative direction of the x-axis times the direction of the x-axis, which is j hat, which is the positive y direction. The force of the slinky tension is equal and opposite to the force of gravity, and it keeps the bottom of the slinky motionless until the slinky collapses and then moves through the air. And the force of drag takes place after the bottom of the slinky is in motion, as it's dragging along the air and there's friction with air resistance. So the force of drag equation is shown here as negative b, which is the magnitude of the drag force, times the velocity of the slinky squared times the direction of the slinky's velocity. So for my observational model, I used a video of a slinky, someone dropping a slinky, and here I analyzed it in Tracker. So you can see I tracked the motion of the bottom of the slinky over time, and you can see that the bottom stays motionless until the slinky collapses, and then it begins to fall through the air. And the data on the right you can see is being tracked, and that data was entered into Excel to be compared with the computational model, which I'll show you the code for next. So here's my GlowScript code that I had for my computational model. You can see the mass of the slinky, the initial position of the slinky, which I got from the Tracker model, and the initial velocity of the slinky was 0, and the time starts at 0, and here's the change in time per step. And this is the acceleration of gravity. You can see that here, and the direction of the y-axis. And this proportionality constant for the magnitude of the drag force was found by changing it until the final position equaled the final position of the Tracker model. And the GlowScript code continues. So here is the first while loop that I had for the GlowScript code to describe the motion of the slinky until the slinky collapsed. So that the slinky collapsed at 5.767 seconds. So while its time is under 5.767 seconds, the force is described as the net force is the force of gravity, which is the weight of the slinky, plus the tension force of the slinky, which is equal and opposite to the force of gravity. And you can see that described here, as well as the velocity update formula right here and the position update formula right here. And here the clock is advancing, and you can see that it prints out the position of the slinky until the point at which it collapses. And after it collapses, this is the while loop to describe that motion of the slinky. And here you can see that it collapses and keeps moving until 8.867 seconds, and the net force for that is the force of gravity plus the drag force, which you can see described here with the equations that I laid out earlier in the introduction. So here you can see again the velocity update formula and the position update formula. The clock is advancing, and the position on the y-axis is printed out at the end. So the data from the observational model and the predicted motion of the drop slinky from the computational model was put into Excel. And here you can see in orange the observed model from Tracker, and in blue you can see the predicted motion from GlowScript. And you can see there's not much difference until the slinky drops, and there's a slight discrepancy that could be due to error in Tracker, or even other discrepancies that I'll discuss in the next slide. The difference between the two models could be due to a couple of differences between the Tracker and the computational model. So the first possible discrepancy could be due to human error when tracking the slinky on Tracker. I might have made small mistakes when tracking the bottom of the slinky, which led to the observed model being different from the computational model. And the second discrepancy could be due to a fluctuation of the drag as the slinky falls, since the slinky is not a uniform object and changes shape slightly as it falls. Meaning the air resistance could have had a variable effect on the object as opposed to a uniform effect as it would on a ball. So for future studies, I would take this into account when taking account the drag force to make a more similar model to the observational model.